What if I told you that the secret to building the next generation of super agile robots isn't hidden in some complex AI code, but it's actually inside your own body? And no, I'm not talking about your brain, I'm talking about the pure, raw mechanics of your muscles. Today, we're going to explore this wild connection between a pretty old school type of strength training and the absolute future of robotics.
So let me ask you this. Can you actually get stronger by standing perfectly still? I know, it sounds totally backwards, right? We're all taught that strength means lifting, pushing, moving. But what if one of the best ways to build certain kinds of strength involved zero movement at all? That question right there is where we're going to start.
So, how on earth is this possible? Let's dive into the science of how you can generate incredible force without moving an inch. A technique that leads to some really surprising results for athletes.
Okay, so the official name for this is isometric strength training, or IST. The easiest way to think about it is to just picture yourself pushing against a wall as hard as you possibly can. The wall isn't going anywhere, and your arm isn't moving, right? But you can feel it. Your muscles are on fire, creating a ton of tension. That's an isometric contraction. You're building strength at that one specific angle without any motion.
So how does this stack up against your normal gym workout? We know, dynamic training. Well, lifting weights is great for building strength through a whole range of motion. But isometrics, they are the absolute masters of specificity. They build a ton of strength right at the exact angle you're training. And here's a huge one. Because there's less movement, research shows isometrics actually cause less overall fatigue.
And here's the real kicker. You'd think an exercise with no movement would only make you better at, well, not moving. But it's the total opposites. Studies show that athletes who use isometrics get real, measurable improvements in super dynamic stuff. We're talking jumping higher, running more efficiently, putting out more power on a bike, and even throwing harder strikes in combat sports. It's kind of mind-blowing.
But, and this is important, not all isometric training is created equal. The way you actually do the exercise, like how hard you push and for how long, completely changes the outcome. So let's get into the different recipes for building power.
See, it's all tailored to your goal. If you're looking for muscle growth, you're going to use a moderate intensity with longer holds. But if you want pure maximal strength, you're going to push way harder. We're talking near 100%, but just for really short bursts. And for explosive power, the goal is to contract as fast and as hard as you physically can.
So you see, it's this incredibly precise and adaptable tool. You can dial in the intensity and the timing to get the exact result you want. And it's this idea, this amazing level of precise muscular control, that's about to take us somewhere completely different.
It turns out the way our muscles can go from being strong and stable 1 second to incredibly explosive the next, well, that's nothing short of an engineering marvel. It's so good, in fact, that roboticists are now trying to copy it to solve one of their biggest, most fundamental challenges. See, when you're trying to build a robot, you slam into a problem that nature figured out millions of years ago. They call it the control problem. And it's all about the tricky relationship between force and stiffness.
With a normal electric motor, like the kind in most robots, torque, which is just rotational force, and stiffness are all tangled up. If you want to make a robot's arm stiffer, you have to mess with the software, which then messes with its ability to generate force. You can't really change one without affecting the other. But in our bodies, it's a completely different ballgame. They're totally decoupled. You can make your arm as stiff as a board without producing any force at all, or you can generate a massive amount of force while keeping your joint pretty loose. This amazing ability is what some researchers call mechanical intelligence. It's the idea that the control isn't just happening in a computer chip somewhere. It's literally baked into the physical stuff, the muscles and tendons themselves. This is why we can do things like catch a ball or walk on rocky ground without having to consciously think about every single tiny adjustment. Our bodies just figure it out.
So how did engineers finally crack the code and copy this incredible system? Well, they went back to basics, straight to Biology 101, and they looked at the simple way our muscles are laid out.
It all comes down to something called antagonistic pairs. Just think about your leg. You've got your quads on the front and your hamstring on the back. They work against each other. To bend your knee, your hamstring contracts and your quad chills out. To straighten it, the quad contracts and the hamstring relaxes. Simple enough. But here's the magic trick. When you need to brace for impact, like when you're landing from a jump, they both tense up at the same time. That is the secret sauce to independent control. In the world of robotics, they call this co-contraction. By firing up two opposing artificial muscles at the same time, engineers can dial in the exact stiffness of the joint. The more they co-contract, the stiffer the joint gets. It's exactly like when you brace your knee.
Okay, so that handles stiffness. But what about actually moving? For that, they use something called bias, and it's really just the difference in how much each muscle is activated. If one artificial muscle is pulling harder than the other, you get net torque, and boom, the limb moves.
So the playbook for these new robots becomes, beautifully simple. Step 1, use co-contraction to set the stiffness you need. Make it firm if you need stability, or soft if you need to absorb a shock. Step 2, use bias to generate the force you need to actually move. And the result? You get a robot that can finally be strong and gentle at the exact same time.
And the results of copying nature like this, they're not just a little better. They are absolutely staggering. This is a game-changing leap forward for both performance and safety. Okay, get this. When one of these robots has to deal with a soft, unpredictable surface, think about stepping on something squishy like sand or foam. It can stabilize itself 200 times faster than a robot using traditional controls. 200! It doesn't wobble around, it just adapts instantly.
And what about hitting hard surfaces? The bio-inspired robot reduces the peak impact force by a whopping 81%. This is a huge deal. This is the key to making robots that can finally work safely alongside us in our homes and offices without breaking everything. Or, us. This chart just lays it all out. On that soft surface, the adaptive, bio-inspired approach is perfectly stable, 100%. Now look at the old methods. Whether they're set to low or high stiffness, they're a total mess. They're wobbling all over the place, with stability dropping down to just 22%. They just can't handle the real, unpredictable world. And this, right here, is why it all matters so much. The goal isn't just to build stronger robots. It's to build smarter and safer ones. By tapping into the mechanical intelligence that's already in our own bodies, we're building machines that don't need to perfectly see and map out the world. They can just feel it and react to it, physically, just like we do. It's a pretty wild thought, isn't it? We started with a simple question about getting stronger by just standing still, and we ended up at the absolute cutting edge of robotics. It just goes to show you that sometimes the biggest breakthroughs come from appreciating the elegant solutions nature came up with a long, long time ago. So, as these robots start to learn how to be more like us, what's the very first human interaction we should teach them? That's definitely something to chew on.